Okay, so here we go. We're starting chapter 2. As I promised, this video will be much shorter. There looks like there's 53 slides that I was able to get this one down to. This will just be a very basic chemistry review. If you feel like at any time you do not need any of the information I'm giving you because you remember it from chemistry, please feel free to skip to the next video. So we're going to begin. Alright, so the first concept in the chapter, the authors take a second to describe what matter is. I have like a touch screen, so I'm going to attempt to see if I can just highlight with my finger really quickly. Oh yeah, it does work. So here's the word matter. And matter is anything that takes up space and it has some mass. So volume and mass equal matter. Alright. More basic chemistry vocab review. So an element is just going to be a pure substance. So it's something that cannot be broken down by a chemical reaction. And then a compound is when you take a couple of elements and you put them together. But they have to be in like specific proportions. And then properties that these compounds have come from the elements that make them. So we're going to see some emergent properties. So here's an example of when you take two elements from the periodic table and combine them, and how a brand new property can emerge from the two of them. So really quickly, let's talk about sodium. So sodium literally is a metal. It's a soft metal. In the picture you can see somebody look like they cut it with a knife. It's not like a I don't know, steel or something like that. The second picture is a picture of the element chlorine. So chlorine in this state here is in a gas. They have it in a jar. And chlorine gas is noxious. Like, it can kill you if you breathe it in. Apologize for the door slam behind me if you heard it. And then sodium by itself is also very interesting. You are on YouTube right now watching this, so if you wanted to, you could pause me and then come back to me. There's some really cool videos. If you check out like sodium in a pond, they have some people who were able to get their hands on some sodium just like this brick. They throw it into the water. It's very volatile and it makes a huge explosion. So let's just talk about the properties of these two elements like as they stand alone. Both of them are harmful. You can't ingest sodium in the state that it's in here, and you definitely can't inhale or take in chlorine in the state that it's in here. But when these two things combine, you get sodium chloride, which is just basic table salt, like that you sprinkle on your food. So it becomes something that's like very innocuous. But remember, in their pure element state, they could be very harmful. So this is like taking taking something and then putting them together, and then a new property is emerging. And again, that's the definition of what an emergent property is. Alright, so in this table, the authors are showing you the elements that are big in the human body. Alright, so these four here are the four that you're going to want to know about. So oxygen, carbon, hydrogen, and nitrogen. They're essential elements. That's what they call them. They're elements that you need in order for your body to function properly. Even these here that make up like the other 3.7%, those are essential as well. So if any of those are lacking, you're going to run into an issue. And then at the bottom here, you'll notice that it says that there's less than 0.1% of mass that is attributable to something they call a trace element. And trace just means like small amounts. So boron, chromium, cobalt, fluorine, iodine, and I'm aware I skipped copper. You can keep reading. But think about when people take like a multivitamin, the minerals that are in there, those are part of the trace elements. It's better just to get all of it from your food, like straight away, instead of taking a multivitamin, but it's just something to think about. Okay, so now we're going forward, and again, you can pause this if it's too fast or if you need to read the slide. So this is on the concept 2.2. This concept and elements properties depend on the structure of its atoms. So first they define what an atom is, and they're going to call it the smallest unit of matter. So you're not going to get any smaller than this, and the elements still have the properties that is associated with it on the periodic table. Once you start to break an atom apart, you're looking at something called subatomic particles. So here we go. These are the pieces that make up the atom. So if we do this reductionism thing, this is like a level deeper than just the atom itself. So the atom is made up of 3 parts. You have neutrons, which are neutral. They don't have any charge. Protons, they have a positive charge. So protons, positive, they both begin with the P. Pretty simple. Neutrons sound like neutral, so they don't have any charge. And then electrons, they carry a negative charge. And the behavior of the electrons is what is going to be allowing the different types of bonds that we will talk about to, exist. All right, here's a picture. They're showing you something that looks like a Bohr model, B-O-H-R. So in this picture, you'll notice that in pink, so the subatomic particles that are pink, so these 2 guys here, and this is the same element, by the way, they're just representing it in 2 different ways. So the 2 pink ones, those are the protons, and you'll notice that these brown ones are the neutrons. And collectively, the center is called the nucleus. All right, and then on the outside, they have an electron cloud in this picture. So that's all of this like yellow area that's kind of surrounding the nucleus. And that's more of an accurate representation of like how an atom would look if you had to, I guess, visualize it. Over here, you'll notice that they put the electrons like on a ring, a circle, a shell, if you will. And this one is not as accurate because we can't actually like pinpoint where an electron is at any one given second. And so the cloud is a more accurate representation because we know that they will be somewhere in that area. If you remember orbitals from chemistry, think about the shapes of those, and what you're supposed to understand is that the electrons are traveling somewhere within those orbitals. All right, now this part here, we're discussing how to read the periodic table, actually use the information on it to be able to tell us something about each of these atoms. So there are a couple of numbers that you'll see. One of them is the atomic number. This one is usually at the top, and it just tells you the number of protons in the nucleus. All right, so how many positive charges are inside of this atom, or not inside of, but like make up the atom. The second number that you'll see is the mass number. All right, and that number is the sum of the protons plus the neutrons. So the whole center, that nucleus piece, that is what the mass number represents. The atomic mass, that's the third number. This is going to be the total mass of the atom with all 3 of its parts together. The electrons weigh like nothing, so it's mostly, it's going to be pretty close to the sum of the protons and the neutrons. Okay, let's keep going. I'm going to tell you how you can find out like just the number of neutrons in a second. So this designation here, how they have it written, this is something that you'll see sometimes on periodic tables. I guess the book maybe will show us more of this, but you're supposed to remember, or even if you don't remember, you can always go back. The mass number is going to be the thing at the top, and then the atomic number they have written at the bottom. This is not how it would look in a block on the periodic table, at least not the ones that you guys have in your plant books or whatever. So the mass number, again, is the number of protons and the number of neutrons. And the atomic number is simply the number of protons. So if I were to ask you, can you please tell me how many neutrons are in this atom of sodium, you would need to subtract 23 from 11. And hopefully you get the answer 12. So there are 12 neutrons. Ooh, yellow's not a good one for that. Let me change back to black. So 12 neutrons in UT. Okay. All right, we're working it out, guys. I can write now a little bit. It's kind of cool. Okay. So because neutrons and protons each have they use a unit of measure called a Dalton. They're saying that the atomic mass of sodium as 23. It's 23 Daltons. Essentially, don't worry about that particular unit of measure. I've never seen it come up like in a test or, you know, nowhere on the AP exam. So don't worry about the Daltons. But if you're interested in them, please go back and look at them. All right, let's keep it moving. We're talking about isotopes. So what is an isotope? This is the reason why I was just talking about the number of neutrons, because isotopes are atoms from the periodic table that have a slightly different number of neutrons than, like, I guess, like the average, whatever atom you're talking about. So it says all atoms of an element have the same number of protons, but they can differ in the number of neutrons. This is a repeat of what I just said, the first one. So here is your vocab word, isotopes. They're different atomic forms of an element, and they differ only in the number of neutrons. If you were to fluctuate the number of protons, then you're not dealing with the same atom anymore. And that is important for this concept here, radioactive isotopes. So, when they say that radioactive isotopes, they decay, it means that they kind of like give off energy. They're releasing their subatomic particles, and that releasing of energy, it could potentially be harmful, it could be cancerous. We have, of course, found a way to, like, I don't want to say exploit this property, but for lack of a better word, we've found a way to exploit this property so that we can use it for some good. So we use radioactive isotopes in things like carbon dating, so dating a fossil. We also can use it to give to someone if we want to trace, I guess, like a metabolic pathway, or process certain radioactive isotopes, like combined with other things inside of the body, and you're able to kind of see the motion of what is happening if you were to do a particular scan. So we'll leave that there, and then that in turn could help with us diagnosing some medical disorders. All right, here's a picture of a PET scan. This right here, this area here, is cancerous throat tissue. So I guess this person was either injected or given a radioactive isotope of some sort, hopefully in a safe level. I'm pretty sure in a safe level. They're not going to try to harm you any further. And they're able to detect some cancerous throat tissue. All right. So electrons are the money for atoms, and by that I mean they are very important. They're what allow, like, these relationships between atoms to create compounds. So what do you need to know about energy? This is kind of like a little bit of physical science review, but I'm sure it was also in chem. Energy just means it's something that can cause change, or the ability to, like, do work. That's the other way that they, like, phrase it. Potential energy literally means, like, if I say you have potential, it means that, like, you have something within you that could emerge and it could be great. Potential is a storage. It's stored up, it's waiting to come out. So potential energy is just that. It is when a compound has some energy stored away that it can use for a number of different things. All right. So when we looked at that picture back 2 slides ago, I believe there were 2 protons in that, so that had to be helium. But when we looked at it, the picture B, the one with the valence shell, or like the electron shell, the one that I said was less accurate, this is what the electron shells, that's what they are. So they describe it as the average distance from the nucleus. Electron shells, you can hold 2 electrons on the first shell, you can hold 8 on the second shell, and then you can hold 8 on the third shell. And I don't think we're going to go too far beyond that. We'll leave it there. But the further away these electrons are, if they get excited, they can actually jump up energy levels. And when they fall back down, they release some potential energy. So I think in this last bullet, electrons can move to a higher or lower shell by absorbing or releasing energy respectively. That's an important concept we'll come back to as needed. So this is just like an analogy. They're saying the ball is kind of like the electron. If it's up high, you let it go, it bounces down the steps, it will come to a complete stop. So the very top of the steps here, that is where the potential energy is as it is bouncing down the steps. That's what they call kinetic energy, or just like energy of motion. And then this here, this second diagram, is supposed to be a representation of what's happening on the steps, but the model is more like how we looked at the atom a couple slides ago. So they have the nucleus, you have your first shell, which is the lowest energy level, second shell, and then the third shell. Remember, this one has taken hold 2, this one is 8, and this one is also 8. We won't need to go beyond that. All right. Electron distribution and chemical properties. You can read this slide. All right, so let's keep going because I'm already at 15 minutes. So here is what I was talking about. When you look at the periodic table, this is more of like what you would see. Atomic numbers at the top. So this number is going to be, it's the number of protons and electrons. They're the same. So helium has 2 electrons, helium has 2 protons. If I wanted to find out how many neutrons the average helium atom would have, I would do 4.003 minus 2, and you should come up with, it's approximately 2. There's a picture of 2 atoms, one of hydrogen, one of helium, and they're the ones that take up that first shell, or their electrons are on that first shell. So hydrogen has an atomic number right here. Remember that atomic number's at the bottom here. Atomic number of 1. So 1 electron, 1 proton. Helium, 2 electrons, 2 protons. Let's keep going. So we're going to the second shell now. So we're looking at lithium, beryllium, boron, and carbon. That's the money molecule right there. So notice that in the second shell, every single one of these has the 2 electrons, and I'll do it in a different color so I can highlight it. The first 2 electrons are always filled. You have to fill that first shell before you can move to the next one. And as we move to the right, notice that the number of valence electrons are growing. And remember, I said that the magic number is 8 for these to be full. So lithium will be more likely to kind of like throw away its electron. Beryllium might do the same. Boron, yeah, could do the same. Carbon likes to share, and so this sharing is what is important. If you come down here and you look at the third shell, pause the video for a second, you can count. You'll see that there's 2 electrons on the first shell. There's 8 that satisfy the second before you move on to the third. All right, and then as far as this is concerned, oxygen was important, nitrogen was important, phosphorus is also important. But these guys here, they call those like the noble gases. So those particular elements, they are completely full. They don't like to share with anybody because they're satisfied. They have enough electrons in each of their shells that they are complete, they're whole. All right, so let's talk about what I was just explaining, that chemical behavior is dependent on this valence shell number. So the number of valence electrons are the number of electrons that occupy the valence shell, that outer ring that we were just looking at. And the reactivity of an atom is directly related to however many unpaired electrons there are. So the more unpaired electrons, the more likely it is to like throw away the electron, meaning it would do well in an ionic bond. When you get closer to having that 8, those are the ones that are going to steal that electron, so also be in an ionic bond. But that sweet spot in the middle, that carbon, for instance, it has 4 and it needs 4, so it's very willing to share, and that would be a different type of bond. That would be a covalent bond. All right, so here we go. This is bonding. Chemical bonds, they're just attractions, one atom to another because of these electron shells. All right, covalent bonds, they share, show sharing. And when you hold 2 atoms together by a covalent bond, that's a molecule. There's a picture of two hydrogen atoms bonding. So here they're separate, and then they're coming closer together until they're one. Here's how you represent it. They draw a line in between the two. This is how they would write it abbreviated. Alright, so this line here denotes a single bond. This is a double bond line. Triple bond would be 3. This slide is just showing you the different ways that they represent it. So this is, they call this one an electron distribution diagram. That's all of these. These are structural formulas, all of these. You'll see a lot of this kind of a thing. So start to learn to read them. And then these ones are space filling models, and these are ones that you can kind of see when we use the modeling kits, what they look like. Alright, again, bonding capacity is related to valence. So like, let's keep moving. I've already talked about it. Okay, so pure elements. Notice that whenever you see like hydrogen atoms, they always come in a pair. And then oxygen atoms, they also always come in a pair. Those are still pure elements. But once you start to do this arrangement of like H2O, right? So you have two atoms of hydrogen and 1 atom of oxygen. It becomes a compound. CH4, that's a compound. Methane. Let's keep going. Alright, electronegativity also is going to help with some bonding. So an atom's attraction for the electron of a covalent bond is what electronegativity is defined as. So oxygen is a very electronegative atom, and those are the things that kind of help you create some of these covalent bonds. So non-polar covalent versus polar covalent, what does that mean? Non-polar covalent, they are equally sharing, so share the electrons equally. Polar covalent, however, they pull one way more than the other. Water is a polar covalent molecule. The oxygen has a greater affinity or love for those electrons than the hydrogens. They're just smaller. So here again, one atom is more electronegative. Atoms do not share the electron equally. So you get these partial negative and partial positive charges, and this is how they designate those. So you see this fancy little sign with either a plus or a minus, they're saying that it's a partially negative or partially positive charge. Again, oxygen is more electronegative than the two hydrogen atoms, and this is one molecule of H2O or water. Alright, ionic bonding, that is when one electron is going to chuck an electron and the other, one atom will throw an electron. The second atom will be the receiver. And they're kind of happy together to, like, you know, distribute an electron and the other one to receive one. So after the transfer of an electron, both atoms have charges and are called ions. You see these designated like with a plus or a minus up in the right hand corner, like a superscript kind of a thing. So the most famous example is the same one that we just were looking at the picture of. Here's sodium, an atom of sodium, an atom of chlorine, and you know about sodium chloride. Sodium chloride is ionic. The cations are positive, anions are negative. I guess the way that I've remembered it is that the anion has, like, the second letter is an N, so I think negative. And then if you want to, you can pause and go back and look at the initial, like the first block that you saw with, not block, but like periodic table you were looking at with the valence shells, and you were looking at sodium. You can go back and you can count, or you can count here really. But basically sodium's first shell is full. So sodium's like, okay, yeah, that's all good. So their first shell it has the 2, good, done. Then, but when you look at their second one, it has the 8, so that one's happy. When you go to their third shell, remember, this can take up to 8 electrons, but it only has 1. It is easier for sodium to get rid of that 1 electron and give it to chlorine. Notice that chlorine first shell is full. The second shell is also full. The third one is it's missing 1. Again, that one also needs 8. So once you transfer that 1 over, so as soon as sodium gives it away, just like in the before, everybody's happy, and you create sodium chloride. Okay, cation positive, anion negative. Ionic bond is the attraction between the two of them. All right, ionic compounds, they make what we call salts. So here, compounds are salts, ionic compounds are salts. Salts like sodium chloride, table salt, they are crystal-like, so they take on a crystalline shape. All right, now we're ranking bonds, like as far as their strength goes. What is the strongest thing? So covalent bonds are going to be our strongest. And then we're going to have some weak bonds. But what's interesting is that a lot of biomolecules, they're kind of held together by weak bonds, and it's really ingenious because if they were held together by a stronger bond, it would take more energy to pop them apart, which is less efficient. So for efficiency's sake, sometimes the weak bonds they can be the better bonds, and I'm saying that with air quotes. Van der Waals are just interactions that happen because the atoms are smushed so close together. All right, so let's talk about one of the weak bonds. Again, I'm doing this in like air quotes like you can see me, but anyway, hydrogen bonds, they're happening because of that polarity in the water molecule. Basically, when the electronegative part of water, which is oxygen, comes into contact with another water molecule, it will kind of like try to pull at the hydrogen of the second one, and that attraction creates these bonds called hydrogen bonds. So here we go. Here's a picture. So here's the electronegative oxygen. You have these two slightly positive charges on the hydrogens. Here, it's not water bonding to water, it's water bonding to ammonia, but the idea is the same. The more electronegative atom is pulling on the partially positive one, and the two are linking. And so that would be a hydrogen bond. All right, weak van der Waals. They're, again, when the atoms are really close together in a molecule, they stick. To give you the example of a gecko's toe hairs on a wall surface, that's why they're able to walk up walls. My sister just walked in. Do you want to say hi? My students. It's a recorded lecture.
Hi.
Okay, she said hi. Now she's saying, she's like, what are you doing? Okay. Okay, so molecular shape and function. So this one is where we're gonna like take it next. We'll explore why the shape of a molecule fits its function. This is really interesting. So I left these two in, not this part anyway. We'll talk about why. Actually, here's a question for you guys. Why do you think that this has this particular arrangement? Why is this arranged the way it is? I'm not gonna give it up. I'm going to leave that open. Maybe it's something we can discuss in the first 10 minutes. All right. This one, again, is just repeating more of the same, that these molecules can interact with each other based on their shape and whatever purpose they serve. It'll give you a different, or maybe not a different reaction or effect, but like, I don't know. This is a great example of what I'm trying to say, but I'm losing words now because it's getting late. All right, so here we have a natural endorphin. Think about running. You hear about people getting a runner's high, right? So that is a natural endorphin. It's just being pumped, and it kind of binds with some receptors in the brain. And then you'll notice that next to it, they're putting morphine. So for those of you who do not know, morphine is a drug. It can be synthesized from a plant. We have some forms of it now that are not synthesized from a plant. They are man-made things. So what they are pulling your attention towards is this one part of this molecule. Okay, so in this one part, you'll notice that the atoms are arranged in the same way. And my husband just walked by, sorry. And in this, because they're arranged the same way, they want you to pay attention to this particular portion because that is where these molecules will bind with the receptors in the brain. By them being so close, they kind of mimic each other. So here is a brain cell. This region here that you're looking at, this is the cell membrane. These are proteins that are like embedded in the cell membrane. So in here, this is the inside. All right, so here you have your natural endorphin. There's that one region that I was just pointing out. So I'm going to do it in red. see if I can here, right? That's that one region. Notice how in morphine, it's able to bond the same exact way. And that can be a very dangerous thing. I'll go back to that later. Just let's keep going with the just basics of chemistry here. So for this slide, they give you a definition of what a chemical reaction is. So you're making and breaking bonds. That's it. The reactants are the stuff that kind of start, and then the product is what you get at the end. Here's what a chemical reaction looks like. So you have the reactants here. This is the reaction. Notice that the arrow is pointing one way. That's important. If you ever see an arrow that goes like this, one this way and then one this way, it means it's reversible. This one we're not worried about right now though. So look, I'm just gonna, ooh, I have an eraser, guys. Boom. All right, let's keep it moving. All right, this is 2 hydrogen atoms and then diatomic oxygen is what they would call that. And it's making, you guessed it, H2O, water. Here's another important chemical reaction that you'll come across many, many times. If you've taken bio, you should know this chemical reaction. This is the reaction for photosynthesis. So 6 molecules of carbon dioxide plus 6 molecules of water will yield 1 molecule of glucose and 6 molecules of oxygen. Hold on one second. All right, photosynthesis reaction done. All right, we're almost finished. All right, chemical equilibrium. People tend to think of this as like, oh, the reaction has completed, it has stopped, and that is not in fact what it is. There's actually some backwards and forwards that is consistently happening during chemical equilibrium. It's just that the rate at which things are breaking apart and reforming is equal. All right. Okay. This is it. This is it. This is the last slide. The next two, I think I should have taken this one out because concept 2.5, hydrogen bonding gives water properties. That is for the next chapter. I will actually come back to this very slide and explain to you what that is. Oh, and I think I know why I kept this in. So this is showing you hydrogen bonding between water molecules. All right, ladies and gentlemen, that is it. I cut this down as much as I could. This is a total chemistry review. I went over bonds. We've talked about how to read the periodic table, why atoms have the properties. They have emergent properties. That's it. So the next one will be all about water, and then I think I may be able to split that one into 2. So we'll see. All right. Thanks, guys. Bye.